evening and welcome to another ASV AstroTalk, our September AstroTalk. Back in the stream room, not in person this time. We didn't have our media guy to help us, so we're doing it ad hoc from the comfort of home. Tonight we'll be treated to an amazing talk by ASV member Bruno Zielke on the nature of time. But before we begin, I would like to say that in the spirit of reconciliation, the Astronomical Society of Victoria acknowledges the traditional custodians of country throughout Australia and their connections to land, sea and community. We pay our respect to the elders past and present and extend that respect to all Aboriginal and Torres Strait Islander people today. The ASV loves to bring you these talks, which we do, and we couldn't do it without your support. So remember, if you're enjoying tonight's stream, on Facebook, you can donate stars. On YouTube, you can donate stickers, and all donations, no matter how small or large, are welcome. And if you're watching this for the first time, don't forget to subscribe or follow us on our Facebook and YouTube pages. With the formalities out of the way, let me introduce you to tonight's speaker, Bruno Zielke. Bruno is a retired information technology consultant who studied computer science and applied maths at RMIT and has spent 17 years as a member of the Cosmology and Astrophysics group at the ASV. Bruno teaches history of the universe and related cosmology topics at U3A and CAE and has presented papers to astronomical conferences and has given over 160 lectures on similar topics. In tonight's topic, Bruno will talk about how we measure time, our perception of its passage, how the concept of time has changed, classical and quantum physics view of time, is time necessary or an illusion? Is it possible to travel in time? Paradoxes of time travel, and is time endless or specific to our universe? And when and why does time appear to slow down or stop? And without further ado, I will bring Bruno into the stream. Bruno, welcome.
Thank you, Mark.
Now, would you like to begin your talk?
Okay. Well, good evening, everyone. When I present this topic, the nature of time, to U3A, I normally show and talk about a much watered down version. By the way, can you hear me very well? No idea.
Yes,
okay.
Yes, we can hear you.
I present a very much watered down version. So considering that I'm talking to more experienced people here, I looked up the proceeds of the Time in Cosmology conference, which happened several years ago. So I beefed it up a little bit. And there will be some terms I need to explain in physics. Some of these will be very familiar to you, and some might be new to other members. So be patient with me. Next, the first slide that you are looking at, no, not this one, the previous one. Here we have the what is known as the Foucault pendulum. It was used to study the repetitiveness of the orbit of the Earth. And on your right image, you have a clock that hangs on my wall, which I bought in an op shop for $1. I liked it. Next slide. Okay, so what is time? I listed two cliches here. Time is what stops everything from happening at once. But the one I want you to remember tonight is that time is what we measure with clock. That is the formal definition of it, and we shall return to it time and time again. All kinds of clocks, mechanical, electronic, atomic. Now, time has a duration, it has a price. We think that we feel the passage of time. When it comes to present moment, we probably don't feel it and don't notice it, because by the time you become aware of it, it's already gone. So essentially, we always live in the past. Time provides, in a classical sense, a certain sequence of events and hence memories, which are also stored in that particular sequence. Mathematically, it's in single dimension. It goes one way. We'll talk about this some more. And the distinction between time and space gives us a perception of cause. Now, this concept of causality has been eliminated in quantum mechanics, but it persists in classical view. Now, I should stress that most of us still think in Newtonian terms. Space is out there and objects are in space, and time kind of bubbles along in a sequential manner. You'll find that that is no longer so. Especially the concept of arrow of time, which is only supported by the second law of thermodynamics. I think you are mostly familiar with that. And that is the only instance where the asymmetry of the direction of time is actually formalized. Self-organizing bodies such as biological organisms or galaxies or even bigger structures, they tend to advance towards complexity through act of gravity, and in the process they generate entropy as a byproduct. Next, please. You there, Mark? Thank you. Here are some ancient clocks. The one at the top left has a strange history. It is supposed to be the oldest known sundial in the world. Sundial was initially invented in China, but it found its way to Babylon, and then when Babylonians had battled the Egyptian armed forces, they probably lost a battle, and this one might have found its way to Egypt. It was actually unearthed in Egypt. The Egyptians also invented the water clock here with the dripping water, and the Chinese also invented the clock for measuring the sand glass, I should say. Yeah, the medieval monks measured the time by how long the candles burned, and they marked some passage of time there. Now, they were much older devices, shall we say, such as the Stonehenge and some of the Mayan ideas, which were used more as a calendar to mark seasons for planting, for not planting, and so on. Okay, next one. Right. With the invention of the pendulum clock depicted in the top left, where you have a spring which contains the potential energy to do work, and through a ratchet indicated in the second from the left diagram, it releases that energy slowly, advancing the clock. At the bottom left, we have the famous naval clock. Sometime in the 17th century, when the British Navy, both commercial and military, were expanding their travels, they had difficulty pinpointing exactly where they were, because it was impossible to tell what time it was in their locality due to the pitch and yaw of the sea. So the Admiralty announced a competition, which was won by a fellow by the name of John Harris, who constructed this clock, which was very, very accurate regardless of the weather. It was a fantastic mechanical achievement. In the middle, we have two clocks situated in the city of Prague in Czech Republic. The top one tells foretells the seasons, and the bottom one is just a time clock. On the right-hand side, we have what's known as a 10,000-year clock. It's a mechanical clock which is designed to be accurate to 1 second in 10,000 years. Goodness knows why anybody bothers to construct something like that. It must be expensive when we have very accurate atomic clocks now. Next, please. And here's an idea of an atomic clock. You can see by the number of decimal points that there's a considerable accuracy suggested there. It's based on the vibration, or physicists call oscillation, of the atomic clock. Now, what do I mean by oscillation? Whether it's a pendulum or vibration of a particle or oscillation of a vibration of an atomic clock, the entity, say a pendulum, departs from a stationary position. It goes to its maximum in one way and then returns back to zero and goes the opposite way and returns back. This is called one cycle. And this is what clocks measure. Clocks measure the change in the state of the entity that is actually measuring. Next, please. Now, the concept of the universe as such has also changed during time. Newton regarded the universe as a mechanical clock, shown at left. In the 19th century, we thought universe was an information processor. Here depicted are ones and zeros, which is the normal way with digital computers, but it probably doesn't work like that. It's more in terms of information stored in tiny magnetic fields. And by the way, when we're talking about information, quantum information, it refers not to whole encyclopedias which are thrown into a black hole and then return as a book, but rather information which is related to quantum particles, and they include the angular momentum, also known as a spin, electrical charge, and of course the energy. At the bottom left, we have a mathematician's clock. I'm not sure who actually constructed it. This was in response to Max Tegmark's suggestion that the universe follows mathematical laws. So at the top there, you have a square root of 17, which happens to be 12. And on the bottom, the hour of 6 is shown as a factorial 3. 3 times 2 times 1. And bottom right shows a new concept known as the holographic principle. The bottom part, the flat part, represents the flat part of the event horizon of the whole universe, which is so large that it can be regarded as a flat plane. And then the information which I just mentioned is magnetically projected onto us in 3 dimensions. It is still beyond me how to explain that process, but Maldacena and de Hooft, who are string theorists, they are very firm about that, and this concept is actually taking some tract. Thank you, Mark. When Einstein announced his theories of relativity in 1905 and 1915, artists such as Salvatore Dali and Pablo Picasso and others picked up the idea, and they started painting in that sort of genre. So Picasso, for example, invented the concept of cubism in painting, and he would, for example, paint a portrait of a man which consisted of a number of triangles and squares, and the human eye would take some time to construct the face out of that and perceive it as a portrait of man. Dali's painting reflects the psychological effects of the flexibility of time, and also the fact that we remember the sequences as we perceive them. You probably know that the brain does not in real time actually process all the inputs that you have. Right now, you may hear your kettle boiling, some radio may be playing, you're hearing to my voice, you're fiddling with a pen, You're aware of sitting in a chair. All these things are feeding information into your brain, and it selects out of this stuff to make sense to you. Now, during our lives, we perceive reality through the five senses: touch, smell, and etc. And the brain constructs some kind of sense out of that. Now, through our life, we acquire lots and lots of information and store it in the brain in memory as in a what we might call a mental database, which we call common sense. If what you hear and what you see agrees with the story that the brain presents to you as a result of all its processing, then that makes sense to you. And if it doesn't, you say that's nonsense. Okay, you probably noticed that when you watch pictures of modern art and read some of the stuff about quantum physics. We also this is the lines shown at the bottom here relate to a concept known as the block time in quantum mechanics. By the way, the concept of quantum mechanics is a historical idea when we have mechanics institutes and mechanics this and mechanics of heat and mechanics of everything else. So the name kind of has stuck, but in reality it's quantum physics. So the block universe, which I'll talk about in a moment, is a concept where the present and the past already exists, and we move through it through now moments, the moments that you experience or become aware of it in your past that are happening right now. And these moments are relegated to the past, but the brain reconstructs them in some kind of sequence and produces a real-time film to you. So you remember being a young child playing with the ball or going to the beach for the first time. You remember your mother's voice, that sort of thing. Thank you, Mark. The reason why I asked Mark to change slides is because we tried it with me changing it and we had some difficulties. Now, perception of the actual flow of time, which we experience subconsciously, varies with the speed of the events. When you are in an accident, shown at the top central or a near accident slide, then time tends to stop. It's like you're about to have an accident and you're quite cool. You stop the car, the other guy shows his fist at you and walks away, and only after that you get the shakes in the knees, and time returns to its normal flow, as it were. Like when you come off a bike, it seems to happen in very little time. I included the slide of a rock climber here, because as a young man, I used to be a very active climber of some note. And I want to tell you that when, as a rock climber, you have a fall, you fall down from above your last protection, which the piton or whatever it was is attached to the wall. You fall that distance plus 2/3 of the stretch in the rope, plus all the slack in the rope as well. So you can see that the rope seems to elongate as the climber is falling. She is quite aware of the time passing, but very, very slowly. I actually watched the wall going past me upwards at a very slow speed, and people screaming at the bottom of the rock watching me were talking in very low voices like that. Yeah, she's already stretching her legs to meet the rock to minimize the impact. Thank you. Clocks are also sensitive to speed, as are our bodies. Usain Bolt, for instance, ran 100 meters in under 9.6 seconds, but the watch that he was wearing actually shows less time. It would show less time. You can see that the time is 57 seconds. 9 seconds, 0.57, not 58. Now, how good is that clock? Whether it was right on time, it's hard to tell. But the fact is that even at that human speed, it is possible to register by very accurate clocks the difference in time. And if all the other runners were wearing the watches, then each one would show a slightly different time from that which is recorded by the judges on the ground. This is the workings of relativity. Their time, according to, as compared to the ground time, which was stationary, would be less. Less time would have passed than the clock that the judges were looking at. I will talk about time dilation in a moment. Yeah. Thank you, Mark. Okay, here we have a nice little poem by a Roman poet, Lucretius. He was actually quite a dude. I've looked up his book, and he had a lot of fast-forward ideas in his time. He said, and likewise time itself cannot exist, but from the flight of things we get the sense of time. Now man we must confess, feels time itself, but only knows of time from flight of rest of things. Very advanced idea. Now, at the diagram in the left, I have here a stack of sheets of paper which represent slivers of now time. And on the right-hand side is the sort of a variation of the Minkowski triangles of past and future, with now in between where the lines cross, with time shown vertically and space shown horizontally. So if you sit still, you still travel in time vertically in a straight line. But if you happen to wander about like a fly on the table, then you and your friend, as shown here, would register space-time versions of that trip graphically, which are known as world lines. And that is the basis of the concept of space-time, as Minkowski has proposed it. Thank you, Mark. Okay. I mentioned that time is defined as that which clocks measure. Now, a measure of time is a function of change. Motion of any sort represents change, whether the change is chemical or mechanical or any other change, pressure, volume, whatever, then this change is a result of some processes, what we call loosely as causes. Now, in relativity, special relativity, the faster an object moves, the more the time appears to slow down. So if any of these clocks, if say the clock at the left, on the top left-hand corner, started traveling faster and faster, then the time would slow down. Here, it is not shown in the correct sequence. Likewise, when an object approaches a large body of mass, such as a planet, star, or better still, a black hole, then time appears to slow down to the observer. Now, you've probably heard about the astronaut that falls into a black hole, and you've seen pictures of them hovering above the black hole's event horizon. In physical reality, that would never happen because there's so much violence going on over there that well before he would approach the event horizon, his body would have been ripped apart and atoms separated into elementary particles and then once past the event horizon, converted into energy. So we can't duplicate that effect of him slowing down and hovering there for a while and then kind of dissolving, which is what special relativity observer would see. Now, however, because time is a function of change or motion, when motion stops, the concept of time ceases to exist, as in bottom right. Now, we have three different scenarios suggested for the end of the universe. One is where gravity wins over the dark energy, which is trying to expand it, and contracts it, and we have another Big Bang. Another one is where the universe keeps on expanding, but gravity has not enough strength to bring it back. As you know, gravity diminishes as 1 over distance squared. So twice as far away, quarter the gravity, 3 times away, 1/9, and so on. So in such a case, when the gravity does not have enough strength, we would of course, all of the stars and everything would burn out, and then the universe would just die in what is known as heat death, in near zero temperature, or actually very low temperature. The third scenario is one of known as a rip, where if the dark energy does keep on expanding forever and ever and accelerating, it'll rip apart everything, atoms, and even elementary quantum particles will be converted to vibration of energy. However, what doesn't stop is the fluctuation of the elementary quantum particles in their field. That never stops. So even in near zero temperature, that is almost always there. But euphemistically speaking, when all motion stops, the constant of time also, as we know it, ceases to stop. Thank you, Mark. Okay, now let's come to the difficult part. I want you to imagine that you are on the train and you're shining a torch with a beam of light pointing upwards to a mirror, and it comes back to a detector at the floor of the train wagon. Obviously, you can imagine there are some difficulties with that physically, but let's just forget about that. Now, the traveler on the train, the male in this case, let's say, sees the beam going up and down. In actual fact, because the train is moving, the beam travels up it's probably some kind of curve, and then at the next destination D2, it comes back to the mirror. This is what the observer would see if she could see fast enough. Now, when her clock is running at a standard stationary time, very fast, but his clock, because he's moving, runs slower. So when she looks at his clock, she registered a lesser time expended in that exercise than hers. Now, here's the kicker. Both of them register 1 second duration. Let's just say it was 1 second, or 1 unit of time. Both the traveler and the lady standing on the ground. But his second takes longer to accomplish. Do you get the idea? This is known as time dilation. In street parlance, it is referred to as slowing down of time. Physicists don't talk like that. Okay. There's another interesting effect here. The traveler's body experienced a slowdown in all of their processes. So his his second takes longer to accomplish. Okay. On top of that, his body will shrink in the direction of the travel, and so does the clock, as the diagram at the right show. This is particularly evident in the Large Hadron Collider. As you know, there are three acceleration paths, circular path where they release the hydrogen from the bottle, electrons are stripped, they go into the first accelerator, second, third, and then there are two beams traveling in opposite directions with four areas where detectors are placed where they cross path. Now the beams travel in let's just say 100,000 bunches, and as they approach the speed of light, and they travel at 99.49% of the speed of light, they are actually like pancakes. And then there's a gap, and then in the next fraction of a second, a tiny fraction of a second, another 100 pancakes arrive, and they crash into each other, and 1 in a billion of collisions of the particles of the protons actually hit head on, and this is the these are the reactions that follow from that are studied in the different detectors. I think that's about all I need to say about that. Okay. Right. Just let's go back to Newton's time for a moment. He believed that time ticked at the same rate everywhere in the universe. Now, if you're thinking of absolute time, that the time was the same everywhere in the universe, then from an observer point of view, it is still not the same. It just ticks at the same rate, so to speak. Now, the clocks on the side don't actually show that because I haven't got a proper image here to show you. But Einstein's theories, the relativity theories, are based on the observer. What the observer sees of an object, of a person or a rocket or a particle that is traveling at some speed or accelerating. It may be accelerating in the presence of gravity, for instance, and the actual time dilation, the, so to speak, colloquially speaking, slowing down of time occurs somewhere close to the speed of light, and also in the presence of gravity. Now here's something new. The diagram at the bottom shows two elementary particles. They look like nuclei, which can be entangled, and their vibration, for example, cesium atoms, can be used to measure time. How this is done, I'm not actually aware, but because they are entangled, they vibrate at the same rate. They are in the same quantum state because they are in the same quantum field. So they are the same. They are in vibrations in the same field, sort of like a wave on water. When you put a stick in the water, the waves are similar because they are in the same media, as it were. Yeah, this is very good. They hope that more and more particles can be entangled. On the last count, I think the limit is at about 1100 or something. Don't quote me on that. But after that, they seem to decohere, and the coherence, the entangledness, seems to be lost. Thank you, Mark. So let's talk a little bit about how the concept of time has changed. Just like money, has no fundamental value itself, but the money in paper or in coins, well, coins have some value, but paper money has no value itself. It's just a piece of paper. It really is a promissory note that the government that issues these papers has enough gold or value in the product of the economy that I can actually cover that if you ask for refund. And because people believe that and have faith in it, it represents some kind of a quasi value. It is a symbol of exchange. I pay you $5, you give me a cup of coffee, that sort of thing. But what I've actually given is a piece of paper or an electronic signal exchanged from my phone or something like that, or a credit card. Now, in the same way, time is useful for measuring change of events. Quantum physicists, most of them now, deny the existence of time altogether, and it's especially the flow of time, the Boltzmann's arrow of time. I think that it's unnecessary. And when I get to talk about entanglement, entanglement actually tends to eliminate that concept altogether. So here we have a picture of an angry physicist smashing a clock with a hammer. So time in physics is suggested now to emerge either from entropy directly. Entropy is really a set of processes which generate energy of lower quality that can no longer produce the work when it was higher energy. For example, a steam engine exudes heat which cannot be brought back to produce more work, more mechanical work. This process is irreversible. In the same way, when you put milk in the coffee, or you smash an egg, or Humpty Dumpty falls off the wall, then it cannot be reversed, but the amount of information which is contained in the multiple microstates afterwards is much larger than it was before, and that information appears to be difficult or impossible to reconstitute. Another theory says, as I mentioned, that time emerges out of entanglement, and there's a new suggestion from gravity. I mentioned before that the conference on time in cosmology was conducted several years ago, and I've read some of the proceeds of that conference, and one guy that really is pushing this concept of gravity is a fellow by name of Kozlowski. Now, at Planck's volume, Planck was a physicist in the 19th century, and at the year of 1900, at the beginning of 20th century, he established the first what's known as a Planck's constant, the H with a bar. It is used in a number of constants now, cosmological constants, known by generic name of Planck's constant. For example, the smallest volume is 1/99 zeros of a cubic centimeter. Smallest length is 1/33 zeros, and the smallest tick of time is 1/44. I used to think that it was 1/43 zeros, but it's now been upgraded to 44. And at that level, there is so much noise that all other dimensions tend to merge into one another, and space and time dimensions tend to lose their identities altogether. Now, psychologists say that the concept of time is a human need, a fantasy that we've created. We learn certain things, like we used to believe that the sun goes around the earth, and we still cling to that. Whereas in reality, it is a series of now moments which are constructed by our minds in a way of continuity. It's like watching a movie in the old film cameras which projected movies. The actual slide of each slide of the film does not change. It's only the movement that creates an illusion. The actual movement of the film that creates a movement, and thus appearance of other things happening, other events happening, and we perceive them happening in time. I tried to explain it to some people, and I said, yeah, I understand all that, but things still happen in time, don't they? Yeah, so it's so ingrained in our minds, this concept of flow of time. In our language, we talk about velocity, rate, we talk about speed, we talk about sequences of things, we talk about all kinds of things that take time, and this word time is so imbued in our psyche and vocabulary, and we have nothing else to replace it with. Many of the concepts in quantum physics, such as the concept of spin of a particle, which does not spin at all, is just a word borrowed from ordinary language. Likewise, the concept of color of subatomic particles have nothing to do with color, and so on. So it goes like that. Thank you, Mark. Okay, I've collected several concepts of time here. There are others, but I thought this will be enough. This is from the conference. The block of time diagram at the top left here, you can see a slider labeled now, and it goes from our past into our future. And every person's now is different. Every one person's past is different, and every one person's future will be different. Now, however, nothing happens. You might say, well, how can that be? Well, think of it this way. You can observe a star 10 billion light years away, which means that the light which it created 10 billion, emitted 10 billion years ago, is just come to your detector, telescope, or your eyes. Now, that means that you are looking into the past. Now, imagine if future beings are looking backwards in the same way, then they are looking at their past. But they will have memories of the past as we have memories of the star or our personal past, but neither they nor we have any memories of the future because our now slide has not gone through it. It's like watching a movie. The film hasn't advanced yet to the future. It's looking at this particular slide at that particular moment. And then in a few moments, you see the future slides. Do you see what I mean? Now, the problem with that, of course, the people who are really rubbishing, and I underlined with a capital R, they say that this concept of a universe is static. Nothing happens in it. It's all there. Nothing needs to happen at all. But obviously, observations don't agree with that. We know that the universe is changing. So that's a dead duck, that one. But in popular literature, you will still find lots of references to the block time. Now, the familiar quantum particles, which are entangled here, which share a common clock rate, are used to explain that their vibrations, because of the entanglement, are actually in sync. Page and Waters conducted a mechanism, and they documented they conducted an experiment, and they wrote up a mechanism to that effect. So what they did, they had a computer model, a toy universe created in a computer with an internal clock and an external clock. The external clock is like God watching the universe from the outside, which is a little bit farcical. But their experiments showed that the quantum particles themselves do not change in the state of entanglement. In other words, well, you do know very well that elementary particles themselves do not change. They are the same. One electron is like another. One neutron is like another. And they do not change in the state of entanglement. What that means specifically here is that the information which they contain about the spin, the energy, and the electric charge also do not change. Now, if nothing changes, then there's no need for time. So time, which comes from entanglement, is not necessary to the outside observer. However, an internal observer would see time to emerge from all that, because the state of the entanglement, while in existence, allows each particle to slightly change because of most likely because of Heisenberg's uncertainty principle. Okay, this one is a little bit complex. Now, Wheeler and DeWitt follow this up, and they notice that there are some difficulties with this entanglement concept of time, or emergence of time out of entanglement of the elementary particles. And they notice that the more accurate you try to predict the position of the entangled particles and their properties, the more infinities it produces, which is, of course, nonsensical. So what they did, cleverly enough, they eliminated time out of the equation. And now everyone says time doesn't exist because Wheeler and DeWitt kicked it out, and the equation doesn't include time. So because of that, time doesn't exist. But once again, in their solution, because there is no time, nothing happens in the universe. In other words, universe does not change, which once again contradicts observations. Now, the more sensible suggestion is one that time emerges from gravity, as in Einstein's general relativity theory. Gravity is the agent of change, compressing matter, forming galaxies, structures, increasing complexity, and increasing the amount of information, and I mean quantum information. And if that can be verified in experiments, there's considerable hope that this may serve as an interface between the between relativity and quantum mechanics theories. Whether we go there via quantum gravity theory yet to be written, or by any other name, some kind of loop quantum gravity, or whatever else. There are several names given to that. Who knows? And while we're on this, string theory came up with this concept of loop quantum gravity, where string theorists consider that in space there are very large and thin membranes of energy, which huge amount of energy contained in each, and they go on for very, very long distances. And when two such planes, which membranes, branes for short, come together and they live in the fifth dimension, you probably know that string theory requires at least 10 or possibly 11 dimensions to make the equations work. When they come together, they compress space, increase temperature, and cause conditions very similar to what we call the Big Bang. Nobody really knows what the Big Bang was, but whatever it was, it has produced effects which we could measure sometime later. From 1 over 12 zeros, we can measure reality with reasonable accuracy. At 1/1,000,000th of a second, we can measure it at great precision. But anything shorter than 1/trillionth or quadrillionth of a second becomes a philosophical or speculation or a computer model. Now, so when the two membranes come together, one concept that string theories say is that they have the membrane, say like a sheet of paper, will have a string attached at one end and freely vibrating at the other, and a different kind of string is shown as a loop, which is joined to the membrane at one end and forms a loop outside of it. Now, a fellow, one of the scientists from USA I correspond with, constructed a concept of a single field where particles vibrate in different ways, and because they vibrate in different ways, they acquire different properties. And he calculated that the waveform of such a particle, which he called rotor, because it rotates. If you cut an apple in half with the string bit at the bottom, that would be the shape of the waveform. Mathematically is known as cos theta squared plus sine theta squared equal 1. And he postulated that on one side, the vibration of the waveform, because he works in wave manner, creates electrostatic field, which we call electromagnetic field, and on the other, it creates gravity. And the reason for that is that on one side, it travels a little faster than light, speed of light, and on the other, a little slower. Now, whoa, we are up against a sacred cow here. Nothing travels faster than light. However, from his equations, he proved Newton's laws of gravity and many others, and he's being taken seriously now. And that may be another way of providing an interface between the two incompatible theories. I rather like the idea of a mono field. At the moment, we have, some say, 17 different fields, like electromagnetic field. We have a strong quark field, and so on. And others say we have 26 fields. There's no agreement about that. Thank you, Mark. Okay, for many, many years now, probably 50 or 60 years or more, physicists have been trying to quantize classical physics. What that means is that phenomena, which is described in a classical sense, were attempted to describe in terms of discrete steps. And I have an example here at your left. I hope you can see my mouse moving. We have four stages, which show a ball being thrown against a wall, compressing, storing, converting kinetic energy into potential energy in its substance, and then compressing and then releasing the potential energy, once again converting it to kinetic energy and going away. Familiar story. Every kid knows how that works. Well, it's a bit more complicated for physicists. They now divided time into 4 distinct hops or now moments, representing the state of the ball, a quantum entity, progressing, compressing, and rebounding with the same equations for energy exchange as before. The problem is that no one has yet managed to quantize time or space, because at the Planck's level, both lose their distinct value, as it were, the uniqueness, the what Immanuel Kant called thinginess of the thing, the nature, so to speak, and both time and space tend to merge into one another, sort of like at a certain stage in a black hole. So while mathematically physicists, quantum physicists, treat time as a convenience, as a way of speaking, as a way of solving equations, because entities are observed as changing in time. So you're probably familiar with the derivatives of a function x, for example, distance to a function of time, dx to dt, and second derivatives and third derivatives and so on. So far, there is no proof that these discrete bubbles of or time slivers can actually be shown in physicality to be discrete. I suppose the famed and legendary quantum gravity might actually come to the rescue here, unless some string theorists come up with an idea better than quantum gravity. So for that reason, in classical mechanics and in general street speak, time is still regarded as continuous, but mathematically, physicists treat it as discrete, as a way of convenience. Yeah. You need to appreciate that when you read stuff. Thank you, Mark. Okay, I have a rather large map of directions into which physics have developed and expanded, purely due to theories which Einstein himself proposed, or mistakes that he has made, or suggestions, or some of which he wasn't even aware, but which came out of his equations. One such that he was aware is something that him and his cohort Rosen called the Einstein bridge. They concocted the idea that if you had two sources of energy, such as let's say black holes, then if there was a way to distort space in such a way using that energy to bring them together. And let me demonstrate what I mean by that. Let's say the two black holes are here and there, and by some effect you can do this, right? And now the black holes appear to be very close, somewhere here, top and bottom, as it's shown in the bottom diagram. Then it is possible that a tunnel might form via what's known as quantum tunneling. Now, some of you might not be familiar with that, and I won't go into the explanation of that because there are many different versions of it. But enough said that quantum tunneling happens in your phone, in your radio, in any electronic piece of equipment, in your GPS, and if it wasn't for that, nothing much would work. So it's a well-established fact and well understood. However, when it comes to this wormhole thing, nothing was well understood. For one thing, the engineering problems are enormous. The throat of that tunnel, by the way, Einstein didn't call it a wormhole, he called it a bridge. That tunnel would need to be, the throat of the tunnel would need to be open for long enough for the passage of an entity that we want to send from one area to another, to shorten the trip, to travel in time, so to speak, whether in the past or into the future, to meet the more intelligent human beings that evolved from us. Now, it is considered by the physicists that this thought would require a considerable amount of what's known as negative energy, and that is usually possible by using antimatter. Antimatter is simply ordinary matter with the opposite charge, such as electron has negative charge, positron has a positive charge. Huge amount of that antimatter would have to be concentrated here, and what would keep it apart from blowing up, I cannot imagine. The other problem that I have not seen written up anywhere, but let's say that an unfortunate astronaut, let's say Romeo, lives in one galaxy and Juliet meets at another, somewhere near their respective black holes. Their parents don't approve of the union, but they decided to meet through the wormhole. Now, let's say that Romeo travels up that, and the first problem he encounters is meeting the black hole. Black holes normally swallow things, they don't eject it. So somehow, I don't know how, but he would have to be ejected by a white hole, which ejects matter opposite to a black hole. So let's say he managed to get into some gravitational field close to the white hole and got carried into the tunnel, got ejected, and then he would come into the gravitational field of the black hole, which is attracting him, which is causing the direction of the travel, and there he would meet his beloved Juliet. Now, I don't know whether their life forms would survive that. So far, it's theory, but then again, flight was a theory a bit more than 100 years ago. So if someone in 1915 or thereabouts, when White brothers produced their first flight down the hill in their biplanes, if someone showed them vertical takeoff, they would think that that's nonsense. That's not possible. So in the same way, Steven Weinberg is encouraging us not to reject way-out ideas which do not make sense to us, but rather consider them seriously, because sooner or later someone will take it up and invent a way to make it work. Thank you, Mark. The time travel produces some paradoxes. Let's say that this is not just a home world, but the line, the red line outside, represents the event horizon of the whole universe. And if you were at some point over here and you're shown a torch, then it would take it some time for the light to travel all around and then show you again, and possibly the back of your head. Now that's one contradiction. Another one is that if this is your home world, then the bridge between them mathematically allows this travel. Now, here we have a nice little poem by Buller. There was a young lady named Bright, whose speed was faster than light. She went one day in a relative way and returned on the previous night. So that suggests that time traveled in a negative direction over here into the past, and she came the night before. Now, Einstein predicted this as a mathematical possibility. Could he have himself perhaps gone into the future, examined his desk, copied the theory of general relativity and came back in 1915 and published it? Or he might have gone and killed his grandfather, and in which case he wouldn't have come back, or maybe he met his younger self. Who knows? These are some of the paradoxes that it produces. Yeah. There are more. Thank you, Mark. Okay. People, since time immemorial, ask themselves, did the universe come in time, or did it come with time. Some of the medieval philosophers particularly puzzled about that. Some models based on the Big Bang, which are saying that ours is the only universe, they say that time began with the Big Bang, space came into existence with the Big Bang, and it's nonsensical to talk about what was before in the same way that standing on the North Pole asking which way is north. This is the only place that is north, because every other direction is south. So other models which allow for multiverse and eternal creation of other universes, sort of like standing at near a small waterfall, say 3 feet tall, and watching the water fall down, and you can see little bubbles forming at the bottom. The bubbles float on the water and burst a little later. One of those bubbles is our universe. Now, this suggests that time is eternal. If our universe came from something, then there must have been something from which it was created. The ancient philosopher in Greece by name of Parmenides said that nothing comes from nothing. That suggests that something must come from something. And on the basis of that, there must have been some kind of vacuum energy in which the fluctuation occurred. And if you want to know, and created a Big Bang, if you want to know more about that, you can refer to my lecture on how the universe began, which is also on YouTube. So at the end of each cycle, at the end of each bounce, as it were, because some believe that we expand, we contract, like sausage. Even the ancient Hindu said that there's a certain regeneration. Whether it's exactly the same or there's some cosmic forgetfulness involved, it's not relevant at this point. But that bounce happens at near zero absolute temperature. Now, Penrose proposed a cosmic conformal model on that, cyclic cosmology, cyclic conformal cosmology model, the triple C, where black holes devour everything, and all that is left is just cold vibrating energy in vacuum. And it is in this vacuum that in one region of space or another, every now and again, a quantum fluctuation of some significance will happen and create another expansion of space, the way our Big Bang was created. And that idea was actually first proposed by Boltzmann way back in 19th century. Let me take you to the sea for a moment. You are on a boat in the sea, and there are huge mountains of water going up and down around you, not in waves, just going up and down. And all of a sudden, it's quiet. You know that you are in the middle of in the eye of the storm. It is in such conditions of what Boltzmann called the lowest level of entropy, or the ground level of vacuum energy, that if the vacuum fluctuation does happen there, then that would explain why the early universe had low entropy and progressed to higher levels of entropy or disorder after that. This makes a lot of sense, but that doesn't make it true. A philosopher by name of Leibniz established a principle of sufficient reason way back in times of Newton. And he said that if it makes sense, then it must be true. Not so in quantum physics, of course. Next one, please. I hope you are thinking of some good questions, because I'm nearing the end of it. This is in a way of a summary. Is time real, or is it an illusion? The case for time being real on the left-hand side is is supported by the second law of thermodynamics, and most specifically by the so-called arrow of time. Processes tend to go one way, even though quantum physicists say that processes can, in theory, go both ways, back and forth, either in the past or into the future. In practice, they seem to go only one way, as described by second law of thermodynamics. What it means in practice is this. The sun belts out a certain amount of energy in all kinds of frequencies, and plants on Earth absorb that energy, and through quantum effects, they convert it into chemical energy, which is then transported to the cells of the plant, and then the plant develops, grows, and dies. Now, most people would say, yeah, well, time makes the flowers grow, doesn't it? And time makes mountains disappear. But there's no time involved here. There are only processes involved, chemical, quantum, physical processes. And this is the concept of thermodynamics. But in popular parlance, we think that there must be time involved, hence this concept that comes out of the law, the second law of the arrow of time. In nuclear reactions between particles, specifically particles called kaons, I won't go into that description, they react, do something, and then reconstitute themselves just as they were before. Now, you could very well argue that through the agency of the weak nuclear force, which is present in every transformation of one particle form into another form, or in radioactive decay, which is the same thing, kaons must have transformed into something else, absorbing energy from the weak field, and they became something else, then they gave up something, and then they transformed themselves back into kaons. That's possibly, but some physicists claim that is a proof that time is real and that particles travel back in time. I don't find that convincing enough. Looking at the arguments against, once again, Leibniz, and he was a philosopher and noted mathematician. You probably know that he invented calculus of functions a little after Newton, whereas Newton invented calculus based on geometry. So it is Leibniz's version that is used today. Never mind. Leibniz said that, and some other people as well, define time only as a relationship between events. That's very interesting. There is no time involved. There are only events, and we perceive it, the sequence of the events, once again, I have to use the concept, the time concept, which is imbued in our language, and then the processes which occur, meaning time, go on in certain sequence. In the same way, physicists say that space is a fiction. There is no such thing as space, they say. Some people say that. They say that space is defined by the distance between objects. Now, mathematically, this is very neat, but vacuum, as far as we know, exists in space, and space, according to some theories, expands. There's a fellow by name of Victor Toth on the Quora forum that believes that that's nonsense, that space does not expand at all. It's the objects that are expanding away, and we think that the space is expanding and carrying them with them, with this expansion. Whether it's a problem of language or this imbued concept of space being the priority entity as a given, or whether it's still Newtonian kind of mindset. At this stage, I couldn't tell. In quantum mechanics, the block universe has all past events, present and future, already existing, and thus there appears to be no change, hence no time. Standard model of particle physics does not list time as a fundamental entity or is given as a priori. Priori is a Latin word that philosophers use to designate something that exists as fundamental in its unquestioned. I think it's quasi-religious idea. That's probably where it comes from. Against time, psychologists say that time is a human illusion, a human construct, because we think we register change sequentially, therefore it must be so. But when the rate of that change ends, time will also end. Now, the interesting emergent time is listed in the third column here. Quantum physicists say that time emerges from subsystems such as entropy. In street language, we call it disorder, which is close enough, but not quite the same thing. Someone asked me once, how would you define disorder? They were particularly interested in the concept of chaos, which is not quite the same thing. And I gave them this picture that if you picture a room, on one hand, on one side, there's a wall full of books, and on the other side, there's a wall with cabinets full of children toys. You let a group of children in for half an hour, and the amount of energy required to restore everything back to the way it was is the measure of that disorder. The reason for that is that the number of, in physics speak, the number of microstates which describe the state before is lesser, therefore there's less information required than the number of microstates after the egg breaks, after coffee dissolves in milk dissolves in coffee, and after the children messed up the room. That information is not recoverable. Other physicists say that time may emerge from entanglement, which we discussed, or potentially with gravity, which makes more sense than the others. Now, those of you who studied engineering or mathematics will be familiar with imaginary numbers, which are based on the square root of 1. This was invented by a Swiss mathematician by name of Euler. He was quite a clever guy, and he came to a problem where square root of -5 could not be transported much further. So he took the square root of 4 and square root of -1. Square root of 4 actually equals 2, but square root of -1 didn't go anywhere further. So he called it little I, imaginary number. And now it is used in every possible science, biological or physics. When that imaginary number I, little I, is attached to a real number, such as 5, 6, or 7, and other numbers in an equation, then it's called a complex number, because it is composed of real numbers and imaginary numbers. And when such an imaginary number is attached to a time symbol and squared, a real number, a real time dimension emerges. I'll describe how that happens. We've described how the pendulum goes to its maximum, comes back to 0, and goes to opposite direction maximum, and then comes back to 0. This is depicted by a sine wave going up above the 0 line of energy, as in positive energy in one direction, negative energy in the other direction, and then returning. So you have the positive cycle and the negative cycle, and that completes the whole transition, one cycle. Now, in order to get the energy of expanded in that, you need to add the two, and the mechanism for adding the two is squaring the equation, the differential equations. It's what's known as a second order differentials, but let's not get lost in that. So when you square the square root of -1, you get -1. And suddenly, when it's attached to the t symbol, you have -t. So time mathematically emerges, the dimension emerges. This is the mathematical explanation of it. You might have a problem with that. Thank you, Mark. Okay, another poem. A clock of life is wound but once, and no man has the power to tell just when the hands will stop, at light or early hour. Now is the time, the only time. You own, live, love, toil with a will. Place no faith in time, for the clock may soon be still. So here we have a clock with a baby advancing into adulthood and finishing up as an old man. Here we have a time traveler image, a galaxy where each direction has a different time. And here is the Brian Greene's concept of time, which can be sliced either perpendicularly or at an angle, depending on the speed of your travel. Next, please, Mark. Right. So I'll summarize what we've talked about. Newton's time clicked at the same rate everywhere. It doesn't mean that the time was absolute everywhere. I think this is a misconception, but at least he said that it progressed at the same rate everywhere. So in a classical view, time has a unidirectional flow, and there's an arrow of that flow known as an arrow of time, supported by the second law of thermodynamics. Clocks measure a change, acceleration, change in pressure, change in direction, and this gives us a sense of cause and effect. Something must be impinging on the entity that is changing its state, and the effect observed must be the effect of that cause. For example, when a car crashes into a pedestrian, the pedestrian is flung off the bonnet. Gruesome. Quantum physicists deny the existing of time as fundamental, and some argue that it might be emerging from the entities that the subsystems I've mentioned. And they still use in the mathematical descriptions time as a convenience. So when you see such mathematics and such expression, beware of the fact that time is a speaking tool. It's a fundamental problem with our language. We have nothing else to exchange the concept of time for the rate of change, in which time is also imbued. So all events in the past and present already existed in Einstein's block time, but that makes the block time stationary when nothing changes. Psychologists consider that time is a human illusion, reconstructed not necessarily in simultaneous time as they occur, but the brain takes time to reconstruct the inputs that it gets from sound of my voice, from the pictures that you read, and the text that you read, the pictures you study, and the noises that you observe outside, and it presents you with a story, a film. you think it's in real time because it happens so fast. Okay. Mathematically, time travel is possible, but it results in paradoxes as based on current understanding, theories, and technology. And considered as a succession of events and of motion and processes, the time stops when all movements stop. And I will also stop here. And if you manage to understand everything, you need not ask anything. But if you feel that something needs to be gone over again, that to my level of understanding, I'm happy to do that.
We have time for a couple of questions, Bruno.
Yep. How are we doing for time, by the way? Have I gone over?
We're a little bit over, but that's okay. We're all good. Marina wants to know, how can we prolong good time and shorten bad moments?
Einstein was once asked while he was visiting a high school, he was asked by students, can you explain your relativity idea in high school terms? And he said, that's very simple. When you're sitting in a class on geometry, time tends to drag on and on and on. But when you're having a soda with your girlfriend, time goes in no time. That's relativity.
Okay, so we have another question here from Shannon. Are there observable instances where we may ever see time appear to move in the opposite direction?
Probably not, because of the second law of thermodynamics. I mentioned that in theory, mathematicians and physicists consider that time, according to the equations, ought to allow processes to unwind. In other words, the egg to reconstitute themselves, Humpty Dumpty jump back on the fence, unbroken. But in practice, the information that is related to the microstates, the more numerous microstates describing the state of the particles that constitute the entity, the egg or whatever, they are too numerous to process again. And for that reason, we have to abandon that. And it appears as if though time goes one way because the processes are irreversible. They are irreversible because the information cannot be reconstituted. That's the best I can explain it. I know it's not the full story, but I'll have to quit here. Maybe someone else has a better idea.
I think it's a pretty good explanation. Shannon again, I think this might be the last question. Can the expansion of space be measured in time if considering that the constant of light operates in a different plane?
Okay. There are several issues related to that. First of all, the constant of the speed of light is related to a particular space, Einsteinian space. So our universe, if we accept the fact that space exists, and for the reason of this talk, let's just talk in classical terms. If space does actually exist, then the energy that is expanding that space, and we, for one reason or another, calls it cosmological constant, dark energy, and by several other names, including some of the ancient Greek terms, then that space tends to expand. But space is not made of material things. It's just space. And space bubbles can expand much faster than the speed of light. That is acceptable to all quantum physics, relativists or quantum mechanics. Yeah. So when the Big Bang occurred, space expanded much faster than light. And then once space was created, objects within the space are restricted to the speed of light dictated by that constant. Now, some physicists say, as a corollary, as a opposing view, that space does not exist, that it is the objects that expand. A problem I have with that, objects cannot expand faster than the speed of light. But then again, no one says that objects within our universe is expanding faster than light. So there may be some truth in that. Do you see what I mean? Space can only expand fast before the universe was created. Space expansion happened before the actual Big Bang process occurred, some many trillions of seconds before. So space expanded. You've probably seen the bell-shaped graph, and then once that expansion ended, this is when Big Bang started. The conversion of the expansion energy into massless particles, and then the universe went through a number of different phase changes, which changed energy into matter, etc. Okay, but within the universe, we now have matter and energy. The energy in terms of photons travel at the speed of light, whether it is gravitational waves or photons or any other radiation. But matter itself, speed is expanding at the sub speed of light velocities. So does that answer your question?
I guess Shannon will tell us in a moment if it answers his question.
It's probably bamboozled.
Well, he said the first one was an amazing answer for the first question about observable instances. So hopefully, that also there you go. That also answers my question perfectly and gives me more to think about. I really like the idea of space expanding before the Big Bang occurred. Okay. There you go. You've answered his question perfectly.
I hope Shannon isn't depicted here, because otherwise he'd be a kid
no,
genius.
I actually know Shannon. That's his child.
Okay.
So, yeah. Bruno, thank you again for another amazing talk. It's great having you on every now and then to give a talk. And I know you've already emailed me with another talk that you'd like to give, which will definitely have you on probably early in the new year, I think. Because we're coming towards the end of this year. We've got plenty of speakers lined up, but I think maybe Feb, we might get you in Feb to give a talk on your new topic. So thank you very much.
The topic will be on the nature of reality. Same mind-boggling concepts.
There you go. People, Suzanne saying many thanks, Bruno. Loved the talk. So everyone was, found it very interesting. So thank you very much for giving us this talk.
Thank you for the opportunity.
And to everyone who joined us tonight, thank you for joining us on this evening's stream. We hope you enjoyed the stream, and we look forward to next month's AstroTalk back at Mueller Hall. To those of you watching at home, remember to hit the like button on Facebook and be sure to subscribe on YouTube so you don't miss our live streams. Also like to remind you all that we have an amazing raffle running at the moment with an EV scope, which is it's almost like a portable astrophotography kit for beginners, where it will live stack images that it's viewing to your iPad or your Android phone or whatever smartphone or smart device you have, and you can do it with up to 10 people can share the same image. So you can have all your friends over at a party and point the telescope at an object and start live stacking it to everybody's smart devices. It's valued at $5,000 and tickets are only $5. The link is on the ASV website. And I think it's on our Facebook page as well, but much easier to find on our website. It's going to be drawn on the 31st of October at our Sea Lake Astrofest Q&A dinner, which reminds me, our 3 public viewing nights up at Sea Lake have been booked out. It's 150 people per night over 3 nights. It's going to be wonderful. But there are plenty of other events with tickets still available. So check out www.sealakeastro.asv.org.au. And before we conclude tonight's stream, I just want to let you know that on the 1st of October, we are hosting a viewing night at Melbourne Observatory for International Observe the Moon Night. Tickets are limited. So if you'd like to come along, be sure to book. Once again, the link is on our Facebook page and on our website, on the front page of our website. Once again, thank you very much for joining us tonight. Thank you for Bruno for speaking tonight. And as the comments are saying, thanks, Bruno. Be discussed tonight with my husband, and no doubt we'll have some debate. What an amazing lecture. So there you go. Wonderful talk. And thank you, everybody, for joining us. And we will see you next month.